Hello and welcome to the Science in the News Spring Lecture Series. We will be getting started in just a couple of minutes, so settle in and we will get started shortly. Hi everyone. Welcome to our spring seminar series. My name is Steph and this is Jess, and we're both the spring lecture series coordinators. Thank you all for coming out tonight. So before we get started, we just wanted to kind of plug some of our other events. So as you guys know, Science in the News is really involved with providing accurate scientific information about some of the big stories in the news. And so we do this in a variety of forums. One of the ways we do this is through our spring lecture series, which you obviously all know about. And another way we do it is through something called Science in the Pint, which is a more informal setting. It occurs on the first Monday of every month, and you can pick up one of these little cards out front here. And that is just a way in which you can informally speak with a variety of scientists about their research, and it's a lot of fun, so we really suggest you coming out and trying that as well. And a final way we're able to communicate science is through our online written blog, which is called the Science in the News Signal to Noise, and we publish articles on a bi-weekly basis, so please feel free to check that out, and it's all on the Science in the News website. And I'll hand it over to Jess so you can learn about what we're going to expect for the rest of the night. Thanks.
So I'm Jess, and we should mention we also have a third coordinator, Andrea Young. And so this seminar series tonight is part of, we have a fall series and a spring series in which graduate students can communicate their research to the public. And this lecture tonight by Anjali is our third lecture in the spring series this year. We have 2 more coming up every other week, so hope to see you there too. And tonight, the format is that we have 3 breaks for questions and then also an intermission break. So we ask that you reserve your questions for those breaks. And also, you'll probably notice Anjali repeating your question before she responds, and that's just to help out our audience at home that's watching through the live stream, in case you're wondering about that. So also, we have a survey out front, which we'd love your feedback on the lecture tonight. And we also have a handout that has some information about our speaker tonight and also some key terms from the lecture and some further resources. So if you haven't grabbed these, please grab them at the intermission. And finally, one announcement to our audience at home. You can submit questions through the form online, and there's also the handout and slides available online. So with that, I'll pass it off to Anjali. Thanks for coming. Take your time.
If anybody wants to make a run for it, this is your first of many opportunities, but probably the last one to do so gracefully. Hello. All right, I'd ask if this mic is working, but that's for the folks at home, so if you can't hear me, I'm very sorry. All right, good night. Good evening. My name is Anjali Tripathi, and I am a third-year graduate student here at Harvard in the Center for Astrophysics, which is over there. If you're interested in learning more about astronomy, not only can you go to some great Science by the Pint events coming up in June, right? There's Dr. Owen Gingrich, who will be telling you about some historical astronomy, and Professor Dimitar Sasolov, who will be telling you also more about exoplanets and their weather, but also during the academic year, every third Thursday of the month, you can come over to the observatory down by Porter Square, and you can hear a lecture sort of like this, and if the weather's clear, you can go up on the roof and look through the telescopes. So I encourage all of you come September to come give us a visit, and I look forward to seeing you there. But tonight my talk to you is about exploring the planets. And before we go into that, I want to ask, who amongst yourselves, raise your hand if you consider yourself an explorer of any kind, raise your hand. All right, most of you, right? I didn't ask what you're exploring, whether that's, what's under the shower tub drain with the hair, or if it's the planets. But I'm really humbled that in my day job as a graduate student here, to be able to explore the planets. And to me, it's really exciting that Columbus, got to go and sail around the world, and here I get to explore worlds that are just far beyond our own. But when you talk about exploration, right, you might wonder, well, where is the thing that I'm going to see? Like, how can I find it? Am I going to fall off the edge of the Earth because who knows if it's round? And then what are these distant worlds like? And so that's what I'm going to talk to you about tonight. So the talk is going to focus on 2 parts. The first half will be how do we detect planets? And specifically, I'm going to focus on so-called exoplanets. These are planets that are found outside of our solar system, so they're going around other stars, not the sun. And it's not until the last couple decades that we've actually been able to discover them. So I want to talk about how we've been able to do that. And then the second half of the talk, after the intermission, will be about what are these planets like? What have we been able to learn about them? So I mentioned that we've only been able to find exoplanets in the last couple decades. And the question is, why is it so hard to find planets? Right? So what you see here are lots of planets. But actually, you don't see them. What you're seeing are all these stars. And we now think that around every star is a planet or multiple planets. And so the reason, though, one of many, why it's hard to find planets is that stars shine, right? They give off light that you can see, but planets don't. So within our own solar system, we're able to see all the planets that you know of, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, because we have the sun, right? The sun is a bright light that illuminates all the planets. If I were to turn off the sun, you wouldn't see this. You would actually see this. In the same way that if I turn off the lights, you won't see me anymore. right? Because the sunlight is there to show us the way. And at intermission or after the talk, you're welcome to pick up some postcards from the Chandra X-ray Observatory, where all the pictures you see there are purely because of the sunlight interacting with the planet. So, okay, so stars shine and planets don't. That's great, but I still told you there were all these planets there, right? So one other difficulty that we have gotten around is the fact that planets are far away. So within our own solar system, if you were coming to a Science in the News talk in maybe the 1700s, all of the planets you would have known about would have ended at Saturn. These are all the planets that you can find with the naked eye that we've known through prehistory, as Wikipedia calls it. But, right, if you were at Science in the News then, you would have heard this really exciting discovery in 1781 of Uranus. And it's kind of cool, the fact that Uranus was predicted to exist partly by a mathematical law based on how far planets were from the sun. So someone looked at some numbers in a series and thought, I think there should be a planet there. And it turns out Uranus did follow this Titius-Bode's law. Now granted, this law predicted some other planets that weren't really planets or weren't really there, but details. Okay, now if you wanted some more current news, in 1846, you would have been really excited to hear about Neptune. And so Neptune is another one of these planets that was predicted to exist, not from the same law, from a different way. And so it was predicted by this gent here, Urbain Le Verrier. And this is a picture I took at the Paris Observatory about 7 years ago. One really cool thing you get to do in astronomy is you get to travel all over the world and use all kinds of fancy instruments. Now granted, this is in the middle of Paris now, so it doesn't see so much dark sky. You can see the dome in the back. But it's still quite exciting. And for reference, this window here looks in here, where this is the original prime meridian. It used to go through Paris. And so the sunlight from the window would reflect here and show you the time of day and the time of the month. But we're getting distracted, right? So big news, 1846, right? New planet, Neptune. And so, right, why was it hard to find Neptune? Well, we've already mentioned this, right? Because it was far away. So even though the sunlight will illuminate Neptune, if it's far from its star, or even just far from us to see, it's harder to see and thus harder to find. So this whole time I've mentioned planets in the solar system, right? That means that they are on an orbit, they're gravitationally moving around the sun. But other planets could be moving around another star. And those stars are going to be much further away. So even if they give off more light than the sun, because they're farther away, we don't see it as clearly. So the question is, how did we get around all these challenges to detect exoplanets? So you might think, well, I'm an astronomer, so I must use telescopes. And you would be right. I mean, I do use telescopes sometimes. If you're wondering what it takes to operate these telescopes, the answer is you sit at some computers. And in fact, all of the work I do, right? You might have come to this series and heard about biologists or chemists who work in a lab and work with things they can touch. The only thing I can touch are the keys of my keyboard and my desk if I feel like it. So this, is a world-class telescope facility, so there are lots of computer screens. At my own desk, you'll find just one. But it's the same setup. So one thing in finding exoplanets is, yes, we need telescopes, but we need to use some amount of sophistication. So I'm going to play a movie for you that actually shows you these lasers coming out of these two telescopes. So this is the Keck Observatory, the world's largest, in Hawaii. And again, right, astronomy, real difficult life. I have to go to Hawaii, I know, for me. And what you're going to see here are these lasers being fired from the telescopes over the course of a night. So you see the sky rotating because over the course of the night, right, the Earth is moving through space and our positions relative to everything are changing a little bit. And you can see that they're focused on some place in the sky. I'll play it again in case you like watching lasers go out into outer space. I know I do. And so the thing is, this laser system is part of what's called adaptive optics. Right? We can use adaptive optics to get higher resolution pictures. So just like you might have a digital camera that you own that's takes better pictures than the camera on your cell phone, right? And that's because it's giving you higher resolution. So the reason we're using these lasers is because by shining them up in the atmosphere, we can see how the atmosphere blurs things in the sky, right? So the atmosphere is kind of and looking at stars is kind of like looking at pebbles at the bottom of a stream, right? With the water flowing past, it's sort of swirly, it's kind of blurry, it's hard to see. But by shining a laser, which we know what it looks like, it's just a single point of light, and looking at what it looks like when it comes back down, we can then say, oh, we can correct our mirrors in the same way that we need to, so that what's coming back from the sky looks like the laser we shined up. And so an example of what this allows us to do is in this movie. So you can see it's kind of blurry when we don't use these laser guide stars in adaptive optics. But when we do use them and turn it on, you can see these brilliant points of light without the blurring. So if we want to find planets around other stars, it really helps to have a clearer picture, right? And so this means that we can then take pictures of stars. Here's a picture of a star called HR 8799. And so I hear some of you laughing, right? Okay, so you might think all stars should have cool names like Sirius and the Sun. But the thing is, it turns out there are lots of stars, right? Within our own galaxy, there are 100 billion stars, right? If we go out elsewhere, there are 100 billion galaxies. And so within each one of those, there are a lot more stars. So what we do is we name it after, the telescope or the catalog that was used to discover it and some number. You'll see this again throughout the talk. But anyways, getting back to poor old HR 8799, who you guys are laughing at, right, you can see that there's this big bright blob, and you can see that Pluto's orbit is just that little dot in there, right? Pluto's not actually orbiting the star, to be clear. That's just for scale. But if we use adaptive optics, then we can actually directly take a picture of this star. We call that direct imaging. And direct imaging allows us to see the star, but here you don't actually see it because we subtracted that off. And we can then actually take pictures of the planets. So if I were giving you this talk 7 years ago, I would have told you we can't actually see planets directly. We can detect they're there through gravity and through other techniques, but I wouldn't say that we could see them. So this is from 2008. And the reason the starlight has been subtracted off is because, as you can see here, the starlight is really bright. So just like it's hard to see things on a sunny day, right? You might have to block out the starlight in order to see what's next to it. By subtracting off the starlight and using these really high resolution images from adaptive optics, we can then find that there are actually these little points that are planets. And if you follow them over time, you'll actually watch them go on orbits around. And this has been done for about 18 systems now. So I want to show you a movie of where HR 8799 sits within our solar galaxy. So you'll see that this movie, created by the American Museum of Natural History, shows you just how far away this system is and how amazing it is that we're able to see that far. So here's Earth, and you're going to see the orbits of the various bodies. So there's the moon. You're going to see all those green ones are the planets. Oh, sorry. Oh, it stopped. No, don't stop. Don't. Okay, right. So everything you see here, by the way, is actual data of the trajectories of the planets at a given time. So you see nearest to the sun is Mercury, then Venus, then Earth. That's why you see us. Wave to yourself, Jupiter, Saturn, Uranus, and Neptune. I feel like I missed one, but there you go. So that's the solar system, right? These are all planets that are orbiting our star. That's the definition. And you can see we're surrounded in space by lots of other stars. You can see the constellations drawn to give you some sense of maybe your favorite constellation. And this is just showing you that the sun, right, even though we think it's the brightest object in the sky, that's just because we're really close to it. If we were further away, it wouldn't seem that bright. But one really cool thing that they've shown you here is that all these blue circles are actually stars that we know that there are planets around. And when I say no, we've actually been able to find some signature of these planets and confirm that they're actually there. So you can see, though, we're going really a very long way from home before we can get to HR 8799, right? These are all other stars. That one, Fomalhaut, we've also been able to directly image planets around it. So you can see we keep going, and oh, aha, HR 8799, a mere 128 light years from Earth. And so here's a better picture that was taken the year after the previous one I showed you. And can anybody tell me something that looks different between this picture and the one I showed you before? Just shout it out. Black and white, gray. Someone said 4 of them. Correct, right? So in the image I showed you before, there are only 3 planets, right? B, C, and D. But now in this image, there's actually 4. And you notice that E is the closest in. And that's because, right, when you're closer into the star, it's harder to see. So this wasn't detected until later when they went back and studied it some more. And I want to give you a sense of scale with this system. Right, so you saw in that original picture I showed you with HR 8799 that Pluto's orbit was just like a dot in the middle. So here the starlight has been subtracted out, but we can overplot some planets from the solar system here. And so what you can see is if I'm only plotting the things beyond Jupiter, right, that Jupiter and Saturn would fit well before the orbit of that last planet, E, that was discovered. So E is a little closer in than Uranus, and D is a little closer in than Neptune. But planets B and C are really very far away. And the reason that we find planets like this with direct imaging is because it's hard for us when we're looking at the starlight to find planets that are close in, right? Since we have to see around the starlight, see around the sun, we can only find things that are farther out. But this is kind of interesting because we find these big planets that are really far from their stars. So far, in fact, they might need to wear a scarf, maybe some mittens or something. So that's this guy that you saw in my title slide. So direct imaging, to give a little recap, is something that we can do when we use adaptive optics, right? The laser guide star to help us correct for the atmospheric blurring. We only started doing this successfully about 6 years ago, and we found under 24 planets since then. And the planets that we do find are really big planets, right? Because you have to be able to see them. And they tend to be far away from their star, because otherwise the starlight overwhelms them. So before I go on to tell you other ways that we can detect planets, I want to ask, are there any questions? They're in the back, sir.
You said in your adaptive optics, you measured the laser light and it came back. Apparently it bounces off of something. So what does it bounce off of?
Right, so the question is, we see light coming back to us from the atmosphere after we shoot the laser up, and we compare that to what we know we sent, and then use the mirrors to correct for that. So the way we can do this is that we use lasers that are tuned to a particular frequency or to a particular element. So what they will actually do is the laser will go up into the atmosphere and it'll excite all of these atoms of sodium. And so then they'll also radiate, and then they'll come back down. And we can then compare that to the single point of light that we sent up. Good question. Yes, sir.
Okay, so the last time that we watched this show on Nova about all this stuff looking for exoplanets, they were talking about this technique of looking at the planet moving past the sun, looking at dimming the light every time the planet goes by.
Oh, no.
So last decade.
Right, so the question is, are you going to tell us about planets dimming the starlight? Is that so last century? The answer is no. And if you wait 2 more minutes, if you don't run away before then, that is the next thing I will tell you about, because that's a very powerful technique. Yes, sir.
How was the resolution using the adaptive optics, say, compared to orbiting telescopes like the Hubble and
Right.
the next generation of telescopes?
So the question is, and if you're wondering why I'm repeating this, it's just so the folks at home can hear, is how does adaptive optics compare to space-based telescopes? And the answer is, depending on what you're doing, it can actually do maybe 20 times better than the Hubble telescope. And adaptive optics is a fairly recent thing that we can do, because not only does it involve a lot of machinery and that kind of thing, but you also have to have really fast computers to be able to tell the mirror how to correct for it. So it actually does very well. I think I'll take one last question for now, and then we'll move on. Yes?
For the planets that you've actually been able to observe, do they tend to follow those laws?
So the question is, do the planets that we discover follow Bode's law? Bode's law is, right, it's like when you're a kid, someone gives you some numbers, right? And they say 1, 1, 2, 3, and you're like 5, is that the next number? So that's a very specific pattern. So people haven't tended to look at whether or not planets follow Bode's law elsewhere, but I'm sure you could make patterns based on what you find. But we actually find planets sort of near and far, as the title of this talk suggests, relative to their star. And part of that is planets don't stay necessarily where they formed or in the same place their whole life. Just like you might like to move houses from the house you were born to, where you want to die. I don't know, might get a bit cramped over time. Same thing, planets move. And so Bode's law would just not tell you very much because you're moving. All right, so more questions I'm happy to take later on. But now we will move along to address this gentleman's concern about what's so last century, except that it's not. Okay, so we talked about how there's a sky full of stars. So here's one star, right? You might be seeing it blinking. And the reason you might see it blinking is because there are planets that are moving past it. And so they block out a little bit of the starlight each time they go around. And this only happens when we are oriented so that we are along this line of sight, so that we see planets blocking the starlight. But if we were looking at the system like this, which is what we see in direct imaging, right, where they're going around, then you don't see the light being blocked. So we can get this blinking effect, what we call transits, when we have a very special geometry. And for those of you watching at home, you will get to have an extra effect in case you couldn't see the movie. So if you are watching at home, you're getting blinded by my flashlight. And right, imagine that this is a star. Oh, and my planet is bouncing away. Okay, right. So if you are looking at a star, right, the same way that direct imaging, you see your planet going around like this, and you know, that's not, oh dear, my planet really wants to run away. Okay, right. The planet is going around the star like this, and you don't see anything. But when you have it in a transit, it blocks some of this light, right? So you might be able to see it in this room. It's more visible on the camera. See the light blinking when something's going in front of it. So the way that we're actually able to turn this into something quantitative that we can use in science is by measuring the brightness of a star over time. So we see that the light from the star decreases when the planet is going in front of it. But then the light from the star goes back to the full amount when the star has moved away from it. And so if we can look for repeated measurements with these dips in light, we can detect that there might be a planet causing that. And so maybe you've actually helped find some of these planets, right? So they mentioned that there's a Science by the Pint coming up soon where members of NASA's Kepler spacecraft will come and talk to you. But maybe you've helped the spacecraft find planets. I don't know, maybe you have. And if not, you should go home and do that tonight. And any other time when you think I could be playing 2048 or something on the internet, no, you should be finding planets. So if you go to the website, planethunters.org, you will have access to data from the Kepler spacecraft. So here's the spacecraft. You can see some people standing, so you can see it's pretty big. And this is a spacecraft. It has a telescope, and it was launched in 2009. So 5 years ago, the spacecraft went up, and its job was purely to stare at a bunch of stars. And the idea being that if it stared at stars for long enough, it might see them blinking. But the thing is, Kepler found so much data that we haven't had time to look at it all, just the scientists. And so there are computers that are looking for planets, but actually we need you to help us find more planets. So what you find when you go to this website are lots of little dots, right? So these are different measurements for the brightness over time. It's not a solid line because it doesn't take data continuously, right? It takes it every so often. And your job is to go and find where there are the dips in light, right? So here you can see them highlighted in red. And this might be because the star is blinking from a planet. So you might think, well, okay, that's nice. I can go and select some points. But will this make any difference? The answer is yes. The first planet that Planet Hunters found, so you guys were laughing at the names for poor old HR 8799 before. This planet is named PH1, right? Planet Hunters 1, first one they discovered. And this was discovered around a really exciting system. So this isn't the system shown. This is an artist's conception, obviously. But Planet Hunters 1, PH1, is found in a system around 4 stars, right? So it's got 2 stars. Oh, okay. It's got 2 stars at the center and another 2 on the side. It's a circumbinary planet, as we call it, because this is a binary star system. And so this means that in the afternoons, if you wanted to kick back and relax on PH1, you could sit, you could have a drink, and you could wait for your 4 sunsets. Now, would you see your 4 sunsets? No, because Planet Hunters 1 is actually a very hazy, mostly atmospheric planet. You wouldn't actually see the sky, really. But this is a detail, okay, right? So we can find planets around other stars looking for these blinking bits of light, and you should go online and help with this effort. But we can do things besides just knowing that there's a planet there. So here is some data that was taken both in Arizona and Hawaii, and I was a part of And you can see that we just look for these dips in light repeatedly over time. And so you can see we looked in May of 2008 all the way to May of 2009, and some more and some less. But by finding these repeated dips in light, we can do things, oh dear, like learning the period of the planet's orbit, how long it takes the planet to go around the star, because that's how frequently we expect it to orbit. And when we see these dips in light regularly, we not only learn how long a year is on this planet, but we also learn how far away from the star it is. So whereas in direct imaging, you can only find planets that are really far from the star, here you can actually find planets that are very close in or very far away. And it's actually easier to find planets that are closer to their star, because that means they'll go around more often and we can see more dips in light. Not only can we find out about how long it takes to go around the star, but we can also find out how big is the planet, right? People often talk about how size matters. Well, on a planet, right, the way you can see this is by how much light goes away, right? Because a bigger planet will cover up more of the star, so you'll have a bigger dip than a smaller planet. And so the fact that we can actually tell the size of this planet is something that we couldn't do as easily with other methods. And there are a lot of other things that you can do with transits, which I won't cover tonight, but I will tell you that it's a very powerful technique. So the question of, are transits so last century? Well, no, they're so 2005, but not even, right? Because we can use it to find all kinds of information about planets, and that's the main way that we're continuing to study planets and their properties in detail. So to recap about transits, right, we look for the dips in the light from a star. And we've actually been able to detect hundreds of exoplanets. So there are now over 1,000 planets. And most of these now come from the transiting method. And so you can go online and help the Kepler spacecraft do this by going to planethunters.org. And if you get past the detecting stage, then you can help us learn more about exoplanets, because there's a lot more that we can learn using the transiting method. So here's a recap of the things we've talked about in this first half, but I'm happy to take more questions. Yes, ma'am.
Asteroid belts. How do they differ from seeing a planet start once blinking the light of the sun? Are they too scattered?
Right, so the question is, how would an asteroid belt compare in sort of causing the light to dim the same way that planets would? Right, so when you see a blink of your starlight, that's not enough to confirm that there's a planet there. So we actually have to look for it in other ways. So Kepler has detected several thousand planets, but they're not confirmed planets. As far as asteroids would go, asteroids are quite small by comparison, so it wouldn't cause a noticeable difference. For a planet the size of Earth going around the sun, that's about 12 parts in 10,000 or something. It's very small. It's much less than 1% of a change in light. So an asteroid would be even smaller, right? Because it's much smaller, so you'd get a smaller dip. All right. Yes, sir.
It would seem that the geometry would have to be pretty precisely aligned, even here with our own moon and sun. And it is uncommon that one will flock together and look at an eclipse. What percentage do you think of planetary systems are so precisely aligned that this system can work?
Right, so the question is, transits need a really special geometry, right? You have to have the planet going in front of the star in order to see this. How common is that? Well, a couple things to note, right? So the probability that you're going to see a transit depends in part on how big the star is, right, and how close the planet is to it. And, you know, I've drawn pictures of transits when the planet is near the center, but actually if the planet goes across the top here or the bottom here, you'll still see a dip in light. It might not last the same amount of time, but that's still enough to see a blink in light. So it's actually not as hard as you might imagine to find a transit. In terms of the actual probability of systems that we expect to see transits in, I can't give you a number on that because we don't know what all the systems out there look like, right? So we can see what we've been able to find. And the answer is pretty good, right? We can see lots and lots of stars with transiting planets in front of them, because even if you have orbits one this way and one this way, maybe you'll have some like this or like this. And so there are all kinds of configurations in which you can see a transit. There's a pretty big angle in which that can happen. Yes, sir?
Are all solar systems
Right, so the question is, are all planetary systems in a plane? That is a great question. That question has bothered scientists like you would not believe. And so actually the data that you saw there from a paper I wrote 4 years ago was partly addressing that. And the answer is that the solar system is very unique, not just because you're in it. I mean, maybe that's why you want to think it's unique. That's fine with me. But it turns out that the solar system is remarkably flat, right? Everything lies within a few degrees of the same plane. We've found systems that are all kinds of inclinations, and so what the standard model is that you have a star when it's born and it comes out of this cloud of gas and dust, and then it all spins around, and it sort of slowly compresses into a disk. And so then you'll have planets formed out of that. So traditionally we believed they always came in this disk, but we actually now find things all over the place. So it might be that after they're formed, different things can kick them into different planes, or maybe there's something we don't understand about this picture. And so that's still an active area of research. All right, any other questions? All right, now don't let, oh, yes, over here.
About the laser, is there a well-defined layer of zodiac you're bouncing off of? And you collect the different transition menus?
So the question is, when you're doing the adaptive optics, when you use a laser guide star, what are you bouncing it off of specifically? Do you know, does it change? And what transitions is that? So there is a specific part of the atmosphere where you get these sodium atoms excited. I'm not super familiar with where that is, but it is a well-defined region. And I'm not sure about the transitions. I don't specialize in that sort of thing. So we can find it by asking the Google, though, I'm sure. Okay, with that super knowledgeable response, I will now leave you to enjoy some cookies for a time. And if you are interested, either now or after the talk, you're welcome to pick up a star chart, which if you go out at night, obviously in the daytime this doesn't work so well, you can hold it up and see where different planets and stars are. Obviously you're not going to see Uranus or Neptune because they're too hard to see by eye, but it'll show you the things that are up this month like Mars and Saturn. And then I don't have enough postcards for everybody, so please only take one if you plan on cherishing it. Part of the government shutdown means that a lot of materials that NASA would normally print stopped being printed. So this is what I have to offer you. So enjoy the cookies and the promotional materials. I will see you when you come back.
Just take a 10-minute break right now, so feel free to enjoy snacks or go to the restroom. And please don't forget to pick up a survey and a handout outside. Yeah, just turn it off, and then when you put it back on later, it'll be F1.
That's Oh gosh, where's the clip? Hi everyone, before I turn it back to Anjali, I wanted to make a special announcement about Science by the Pint. We have our new schedule that's up, so you make sure to grab a flyer before you leave tonight. But we also have, it was very perfect timing that last week the scientists from the Kepler spacecraft got in touch with us about doing a special edition sort of Science by the Pint. And so all the details haven't been hammered out for this yet, but it will be the first week of June, probably either June 2nd or June 3rd, where scientists from the Kepler spacecraft, they're going to be in town for a conference. So they're going to join us at the Burren that night and do a Science by the Pint. So it's going to run like our normal Science by the Pint events. It's just going to happen that there's going to be two of them, additional. So there is one on June 9th, and then we're going to have an additional one probably on June 3rd, which is a Tuesday. But again, just follow our Facebook or be on our website, or if you're on our email list, you'll get all the information about that. So. By the way, I don't think it's speaking of anything. Oh, there we go. Nothing. I mean, that's the one for the room. I did. It doesn't, it's showing battery symbols. I think you're pretty loud. Okay, well, we'll just leave this one here then. All right, so those of you who haven't run away, I applaud your dedication. So as we continue our quest to talk about what exploring the planets entails these days, right? We've talked about how do you find these places to explore, but now the question is, what are they like? What do we find? So as you know, within our own solar system, we have these 8 planets, plus the moon. He feels left out sometimes. And so this is towards the sun, so Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. So these 4 constitute the terrestrial or rocky planets, right? So they all have a surface that you could go and walk around on. I don't advise it in most cases, but you could, and this is why we're able to send spacecraft that can go and land on the surface, that can rove around, or they can stay there. And we've done this since the 70s. But further away from the sun, right, are these bigger balls of sort of gas and ice. We have Jupiter and Saturn, which are gas giants, right, very gaseous. Everything you see here on the surface are actually clouds. There is no surface that you could go and walk around on because it's all just gas. It's like trying to walk on the air in this room. You just fall. And then even further out, we have the ice giants, right, Uranus and Neptune. So you can see that the further away you go, right, you tend to get bigger, and it tends to be a little bit colder. And you can see that we're in here where it's nice and warm. And so if you think about what makes the Earth, right, again, besides you being here, part of it is the fact that we have this, right? The fact that you have liquid water, which can sustain life, is a pretty major fact when we think about what makes Earth special. So we want to know, how do exoplanets compare to the Earth? So before we even consider exoplanets, right, you should know that we're still exploring this question even within our solar system, because we know that there are bodies full of gas and ice in our solar system, right? If you go to moons of Jupiter, you can see, like Titan, it's got, Europa, it's covered in ice, and it's even got an ocean under that icy crust, right? But it's ice on the outside, and you can see it spraying out from the South Pole, just like the moons of Saturn. But even closer to home, right, we study Mars all of the time because you can see it's a little bit closer in, it's a little warmer, and the question is there water that we can find? And so the Curiosity rover, which I've shown here, is currently on the surface looking for evidence of how water might have played a role in Mars's past. And who doesn't love a good laser in astronomy? This is not adaptive optics, though. So when we talk about exoplanets then and finding what's like Earth, the central question we then focus on is, would it even be possible for water to be liquid there, right? Are you so close to your star that everything is gas? Or are you so far out that everything is ice, right, steam or ice? Or are you in this beautiful river in the middle known as the habitable zone. And that's the distance from a star where water could even be liquid, right? So if you're around a smaller star that doesn't give off as much heat and light, you can be closer to that star, right, than you could if it's bigger and brighter. And so when I gave a talk about the formation of the Earth at a Science in the News event in October of last year, the best I could tell you that we could do for exoplanets were actually these systems, right? So there's one Kepler-69 and Kepler-62. Again, Kepler spacecraft found them in the 69th and 62nd objects. And there you can see the habitable zone is shown in green. So the solar system is at top for comparison. And right in our own solar system, you can see that Mercury and Venus and Mars, depending on who you ask, fit within this range. And so you can see that Kepler 69 and 62, right, would fit within their habitable zones in 62, a couple planets. But the thing is, these planets, when you compare them to the size of Earth, right, are way bigger. So even though they're in the right location, they're the wrong size. So if we want to think about processes on Earth, right, as compared to somewhere like Jupiter, not only is it gaseous, but when it's bigger, a lot of things change, right? Your gravity will be different. And so if we're trying to find places that are like home, we want, good location, the first rule in real estate, but also we want the right size home, right? Not too big, not too small, just right. So that's why also the habitable zone is called the Goldilocks zone. So as of a couple weeks ago, though, it's really exciting. They actually found a planet that's the same size as Earth, more or less. You can see that comparison here, and it lies well within the habitable zone of the star. So this is Kepler 186. It's a mere 5 million light years away. And it's really exciting, right? Because now we can check that off our list of places that are within the habitable zone, which was a big question in exoplanet discovery for a while. And now we can also get that the size is right. And so this means that we now know that we're able to find planets that are smaller, right? And you'll remember from the transits, it's harder to find smaller planets because you see less light being subtracted off. That we can now start to research these places and do things that we wouldn't be otherwise able to study analogs to Earth. So before I go on, I just want to ask, are there any questions about habitable zones and water? Yes, sir. Right, okay, right. So obviously I showed you some pictures of exoplanets at the beginning through direct imaging, but everything here on out is all going to be an artist's conception. And so when we use transits and when we know something about the star, we can figure out the mass maybe, and certainly the radius, the size of the planet. And so using these two things, we can figure out the density, right? Is it lighter than water? Is it sort of gaseous, or is it rocky? And so the densities that we can guess are sort of rocky. So that's why it's drawn sort of like you see for, Mars or something like that, hence that idea. Everything else, don't read too much into the mountains and all of that. It's the fact of the matter is that it's just not a big ball of gas the way that you see that they drew these sort of other bigger ones. Yes, Matt. Right, so the question is there another compound or molecule that could be liquid in the habitable zone that could be used to sustain life? Sure, there are lots of things that are liquid on Earth, naturally. But when we think about it sort of from a biological perspective of what do we need to survive, the sort of simplest answer we can come to is water. So that's why we study that. We're not trying to exclude any of the other things. It's just sort of the first place to start looking. Yes?
I think my question has the same direction in terms of the reason that you want, what's the reason that you want planets only a certain size? Are you looking for life on Earth? Do life on Earth is just any life?
So the question is, why does the size of the planet matter, right? And so part of that is you want to have the same idea of the surface and the right density, right? If you're very big, getting an idea of mass, it might be a very gaseous planet. So when you're sort of smaller, the chances are better that you're going to be rocky. And that's something that we're more familiar with life being on, right? Because we don't know of life on Jupiter at the moment. Yes?
Do you know anything about the atmosphere of that planet?
So is the question, do we know about the atmosphere of this planet? Is that right? So we can actually learn a lot about atmospheres of planets, and I'll talk a little bit more about that in a minute. But when we have these transiting planets, right? You see it going in front of the star. You can actually look at the chemicals you see from the star when the planet's not there, and then look at the chemicals as they filter through the atmosphere of the planet. And you can sort of get a sense for what's there and what's not. This is something, though, that we don't do with the Kepler spacecraft. This requires something like the Hubble Space Telescope because it needs instruments, right? It needs spectrometers that can look at the chemistry as opposed to just looking at the amount of light that we see there. So that hasn't been done for this planet yet. Yes, sir?
How accurately do we determine the orbit from the sun towards an exoplanet?
So the question is, how accurately can we determine the orbital distance of the planet? So the answer, you're not going to like this, is it depends, right? In part because nowadays we have better instrumentation and we can do a better job than we could before, right? So now we can resolve differences that are within, 1 part in almost, 100,000 or so. And so we can get things, but it's not just how well we can detect it. There are other things that can confuse whether or not we're seeing it right, because maybe there are a couple planets in the system, right? And they all happen to go around at the same time. So maybe you see a couple stars, a couple planets blocking the light, or maybe one goes around every 2 days and one goes around every 3 days. So every 6 days, right, you think that something great is happening. So there are a lot of sources of confusion, but we tend to do a pretty good job of orbital periods, but there's no finite number on how well we can determine that. There are instrumentation levels that we can detect light or movement to 1 meter per second, but I can't translate that into a period for you. Okay, great. So we've now talked about water, and this is really important in a lot of studies for life, and are we alone, and thinking about that in the context of exoplanets. But actually, I have to confess, I don't focus on this in my research because I don't think we're going to get there in my lifetime, and I am really very curious about what these planets are like, right? So the question is, how do the exoplanets we find compare to what we see in the solar system? So I've sort of mentioned we find ones that are far away, and there are some that are near in, but what are they actually like, right? So I've told you their size and their orbital period, how long it takes to go around the star. But what else can we learn? So there's one kind of planet, and this is one of the first kinds of planets that we found that weren't expected before. So when we only knew of our solar system, we kind of assumed that rocky things were close in, gaseous things were further out. But with these transits and things, we were actually able to find these really massive, really big planets very close to their star. And so since they're gassy like Jupiter, we call them Jupiter, part of their name, and since they're very close in, they're going to get really hot from all that starlight that they're getting. So the very inventive name that astronomers have given them are hot Jupiters. So to give you a sense of scale, right, Mercury is the closest planet to the sun in the solar system. And so that's at about 1/10 of an AU, and an AU is the distance between the Earth and the sun. It's an astronomical unit. So right, here's the Earth I've drawn for scale. If you wanted to know where Jupiter was on this scale, it would actually be outside of the room, right, because it's about 5 times further. So this hot Jupiter, though, is 20 times closer to the star than the Earth is to the sun, or 10 times closer than Mercury, right? So that's pretty significant, right? So when you saw this drawing on the front that I did, you can see that this hot Jupiter, right, he's wearing sunglasses because it's hot there. But the other thing you might notice is that he's got this hairdo the way that our cold friend and our habitable zone friend don't have. And this is the focus of my own research, right? Because hot Jupiters, since they're so close to the star, they have problems that other planets in the solar system and things don't have. So you might talk about first world problems. Well, these are hot Jupiter problems. So the hot Jupiter, right, is getting bombarded by starlight and radiation from its own sun. And the fact of the matter is that when you get, outside in the sun, you might get a sunburn, right? That's some effect of the sunlight on you. Well, the hot Jupiter, right, is going to get this nice little hairdo coming off because his atmosphere is actually going to evaporate. It's so hot, and there's so much energy that that gas can no longer stay bound to that planet. And so this is actually what I study. So you might think, well, it's nice that you can say that with an artist's conception, but how do we know that this happens? Well, we've actually been able to measure and observe this. So here's a little cartoon again with the transit idea, but to show you how we might be able to look for hot Jupiter atmospheres that are bigger than you expect. So here's your planet. And so you'll see that when it goes in front of the star, it decreases the light by maybe 1.5%. This is a real system that they've drawn here. It's HD 209458. So it decreases the light by 1.5%. But it turns out that if you look, not in the visible light that you can see in this room, but if you look in ultraviolet light, right, again, sort of the chemicals that can be absorbed by the planet's atmosphere when it passes in front. So you can say, okay, well, there's this much light, ultraviolet light given off by the star. And actually, I see that that light decreases by 15% when the planet goes in front of it. And that might be because there's this cloud of maybe neutral hydrogen around it that absorbs that ultraviolet light and blocks it out in a way that it wouldn't block out normal light because it's so tenuous that regular light just goes through it. But because it's sort of tuned to absorbing this ultraviolet light, it decreases like that. And so we can look in the ultraviolet with the Hubble Space Telescope and actually see these decreases. And we can look at them using all kinds of light, not just at one fixed wavelength or frequency, but at a range. And doing this, we've actually been able to find that there are these atmospheres around the hot Jupiters that can extend beyond the extent that the planet's gravity can hold it there. So it's actually escaping into space. And so these measurements were first done 10 years ago, and there are still only a handful of planets of hot Jupiters for which we can see this. But just like for detecting the habitable worlds, we have to look at really big planets, right, these hot Jupiters, to see this escaping. Even though it might happen for smaller planets, it's going to be harder to see that. So the way that I can study this problem relies on our models of how it works. Because what you see, right, when you think about a system is just a planet, a ball of rock that's getting some starlight hit on it. But the way it can expand is because if we look at just a piece of it, you have this high energy light, this ultraviolet light, for example, and it's so energetic, these photons are so excited to get busy with the neutral hydrogen, right? This is a hydrogen atom, a proton and an electron whizzing around it, that they have enough energy to actually knock that electron away from the proton. So your neutral hydrogen atom is no more. You're left with this proton, so this ionized this hydrogen ion. And that electron, though, has all this energy. He's like, wee, I have all this energy. I'm going to go and meet all of my friends and all of the other bits of atmosphere. And so that electron then can go off and have all these collisions, and it actually heats the gas all over the surface of your planet's atmosphere. So that's the way that actual heating happens as a result of that starlight. And so we can simulate this in order to get a sense of what we expect. Because even though we can make observations, our observations, right, we've done for maybe 4 systems, and they're very crude. And we want to be able to do better observations. But to do that and to understand what they mean, since you can't go and ask the hot Jupiter, hey, what's the deal, right? And it's not like it's in the lab where we can do repeated experiments. So all we can do in physics and in astronomy is to develop models and then to compare these to our observations and to see how that compares. So the work that I do involves sitting at my computer, as I mentioned before, and dealing with a box with a lot of grid cells. And I say, okay, I'm going to try and simulate what happens to a Jupiter when I put a lot of starlight on it. And I say that I will assume it's, such and such distance from the star, so we can scale back the amount of light that you would see there as compared to if we put the Jupiter further away. And you might wonder, what are these funny colors that I'm showing you here? And what I'm showing you is the resolution that we have of this box. We have the highest resolution around the planet and lower further away. And the reason we don't do the whole box at this little fine resolution where you can't even see the grid cells is because it takes a lot of computing power to do this. Right? So I sit around and play with supercomputers all day, which sounds a lot cooler probably than it actually is. And we can increase the efficiency, right, by only increasing the resolution where we need it. So I used Google Maps to help me illustrate this point, right? So here you are, wave at your Google-ized self. And you can see that when you zoom out, right, Google doesn't really care what's going out here because you are only interested in what's happening in there. So the same way, by focusing on the atmosphere of the planet as it starts, we can resolve that, we can keep it happy, and what's happening in the corners over here, it doesn't really matter. So we can speed up our computation. And even doing this, it takes me like tens of thousands of computing hours to solve this problem. So this problem, though, is by no means complete. I'm still doing my PhD, so I don't have beautiful results to show you at the moment, but I will show you some preliminary results that we've been able to generate. You're going to see a movie. And I should mention that this is work that I'm doing with my advisor here, Dr. Ruth Mary Clay, as well as Dr. Caitlin Crowder in Arizona and Dr. Mark Krumholtz at UC Santa Cruz. So what you're going to see in these things, these are all the same box, right? And this is the planet. What this one is showing you is just what the gas would look like. It's a map of the density, right? So red means there's more stuff, blue means there's less stuff. Here, don't worry too much about it, but you can see that you have a ball of neutral gas, that neutral hydrogen, and you'll be able to see how that moves around. You'll see that when it gets heated, you have this ionization, and so that will change the color a little bit. And here, this shows you the speed at which things are moving, because initially, the planet is just happy to sit there. And what you'll see is what happens when you actually turn on the starlight. And the star, I should mention, right, is off to the left of the box. So you can see that when the starlight turns on, right, I keep messing that up. The planet gas gets heated on the side closest to the star, and then it actually tends to move around. And it just keeps expanding over time because I'm not turning off the star. It's just staying there. But you can see that the gas is moving on the top. On the blue is moving out towards the star because it's heating and it's puffing out. And on the back side, it's also moving backwards because the gas on the back, right, it never got directly ionized. And that's why you see this neutral gas left there. It got moved around by the pressure from the day side of the planet, the side getting heated, to the back side, night. So this might not seem super exciting to you, and that's completely understandable. But the previous work that was done on studying hot Jupiters and modeling them took this problem and did it in only one dimension, right? So that means that you wouldn't be able to see the night side of the planet. You couldn't see the fact that only one side of your planet gets heated and one side doesn't. And it also didn't actually incorporate any of this heating that I told you, right? You might think, well, that's a little crazy, right? Because that's the whole process. Well, people would just say we assume that the gas goes to 10,000 degrees Kelvin, and we'll just watch what happens. So the simulation that I'm doing here is actually meant to try and simulate more realistically by incorporating this heating and the 3 dimensions, which is a very computationally demanding problem, to see how we can compare this to observations. So I've already mentioned most of this, but here are a couple of still pictures that you can see, right, that initially and over time how you have heating on the day side and it moves around to the night side and how this just keeps going. So again, you might not think this is super interesting, but in astronomy, we have no other way of knowing what's going on other than to create these models and compare them to observations. So the idea here is that when we have a really well-developed model, not only will we compare it to existing Hubble observations, of which there are very few, but we can actually then propose and make new observations to say, well, actually, the planet is not in front of the star anymore, but I should expect to see a tail of gas coming off of it. So that gas should actually cause the brightness of the star to decrease. So why don't we go look for that? So that's one of our plans, as well as the fact that a hot Jupiter, over its entire lifetime, it's only, in spite of all of this gas moving off of it, it's only going to lose 1% of its atmosphere, of its planet. So that's not a big deal. But if you were a smaller planet, you would lose a lot more of yourself. And so you really want to know what happens to these balls of gas. Do they become balls of rock? Is that how Mercury came to be? You know, did it used to be bigger and puffier, and it just, you know, got stripped away in its little naked core now? Or what? But the thing is, since we can't study these small balls of rock and dust, rock and gas, because they're hard to see, the best way we can do this is by studying these big hot Jupiters for which we have observations and then can improve our models and go on over time. So to recap what I've told you about exoplanets and what we found a lot of things, right? But some of the things that I find most exciting are the fact that there are places where it's the same size as Earth and water could even be liquid there, which, as I said, a month ago, 2 months ago, I wouldn't have been able to tell you that that was true. And the other thing that we found, right, over the past 10 years that is really exciting and is nothing like what we know in our solar system are these hot Jupiters, these puffy gas giant planets that are so close to their star that their atmospheres are evaporating. And that's something, it's really neat when you see something new, right? And especially when you have no idea what it is, because it really challenges us to think up new ideas of how things form. So I hope that my talk tonight has given you a little idea of what we're exploring in exoplanets. There's a lot more to talk about. I don't have time to go into it all. But you can see that we can detect planets both by directly seeing them. This is sort of the newest and fanciest way. But we can also look at those dips in light to find out all kinds of properties about the planet. And with that, we can find planets that are, in this habitable zone, or where they're so close in that they're evaporating like hot Jupiters. So I'll stop there, but thank you for your time, and I will take questions now. All right, so I see you two have your hands up, but you've asked lots of questions before, so we're going to see, do you have a question?
So when you're doing this pure simulation, the planet is of course a bunch of gas, but are you just sort of simulating outside of the planet? Do you also simulate all of the planet? Or like just gas in the planet? Is there a core of the planet?
Right, so the question is, what am I simulating for the planet and in this box? So first of all, every part of the box is full of something. So the whole box is full of gas. And since I actually don't care about what happens at the core of this planet, I'm only interested in its atmosphere, I just simulate it as a ball of gas. Actually, you can see it better here, right, where it's very dense at the middle and it gets less dense outside. And all we've matched is what the density at the outside is to some observations. But what's inside, I don't mind. Other questions? Yes, sir.
Hot Jupiter kind of form that close to the star. How do they get there?
Right, so the question is, hot Jupiters, what's the deal, right? They're so close in. So hot Jupiters, we believe, can't have formed there. They had to have formed further out because they're so big and stuff. There isn't enough material close to the star, as well as all of that gas, right? It's hot. It wouldn't have done well forming at the beginning because it would have started smaller out. So I believe they found some way to migrate inwards. How? Let's not talk about that tonight. Ongoing research, right? But we believe that they moved in one way or another. Yes, sir, in the back.
What do you know about the elements on how to you often make that element what are the functions?
When you say elements, do you mean chemical elements or like what parts go into the simulation? Okay, right. So in my simulation, I am assuming that I only have hydrogen, right? So the question is what went into it? Because hydrogen is what undergoes this reaction that gives you this ionization. And Jupiter in our own solar system has a lot of hydrogen. And most of the universe, in fact, is hydrogen. A fun fact is, right, you see the periodic table over here. If you ask an astronomer what's the periodic table, they will tell you hydrogen, helium, metals. Everything else is metals because in the universe, like 70+% is hydrogen, 20-some% is helium, and then there's this other 5% or something. That's other stuff. And we don't worry about that. So the simplest case, and actually a fairly good starting point, is just to assume all hydrogen. All right, other questions? I didn't mean to tell you all that you couldn't ask questions, just that I wasn't going to start there. Okay, fine, if you took your question, I see. Yes, ma'am.
As you study exoplanets and look at a bigger view of space, are you seeing any patterns?
Right, so the question is, what patterns are we finding in exoplanets? So the short answer is lots of patterns. And just like with Bode's law, you don't know what to believe is a real physical pattern and what is just something that you're seeing by staring at it too long. One thing that we find, right, sort of asked before, is we used to think, right, that planets, right, when they were orbiting, right, when they were going around the star, that the axis of rotation there was the same as the star, right, because the star is rotating and the planet's going around. So we used to think and see that they went around and that was a line. But we've actually found that a lot of things are misaligned. And so depending on some characteristics of the star, actually what elements are in it and that sort of thing, we've been able to tell that there are some planets for which it's going to be inclined, and that might tell us something about how it formed, as opposed to just being in this disk, the sort of way they might have all been kicked or something like that. So that's one thing that people have been able to study slowly by being able to figure out these axes and these angles. There are lots of other things we found, like, planets, just like stars, don't always have to come in ones. So lots of stars, right, you saw when I was showing you all these Kepler planets, they can come in multiples. So you can get planets that have neighbors, right? You can see there are lots up here. And they can also go around multiple stars, which are all things that we didn't expect before. All right, yes?
Can you talk a little bit about what technological developments see coming down the pipeline that will add to our knowledge of exoplanets in the next 10, 20 years?
Okay, so the question is, what technological developments will enable us to do better? Right, so that's a hard question. One thing that's not technological, but I think will actually really improve our ability to study planets is how much we already know. Right, when we started this 20 years ago, we didn't know about any of this. Right, we didn't know what we would be finding, how big they are, how far they are from their planet, from their star. So the sort of like, where do I look? What do I focus on? Was very hard. And so the fact that we can find planets that are, bigger than Jupiter down to, the size of Earth or even smaller, right? And how far they tend to be from their planet, from their star, is a first thing to do. There are lots of telescopes that are helping us find exoplanets with more advanced pointing and just better technology on it, right? So you might, like Kepler, if you consider your digital camera, which maybe has 5 megapixels, maybe a fancier one is 13, right? Kepler's is 95 megapixels. But that's, Kepler launched in 2009, so it was built some years before that. So the next missions, right, will have even more advanced photometers, ways of measuring light. So that's one way to do it, because then you can look for more precise changes, as well as a lot of things of being able to put spectrometers, these instruments for detecting the chemistry. There are advances being done there, so you can then start to do a better job of understanding what's in your atmosphere and the chemistry there. But we aren't going to be sending anything out to any of these stars anytime soon, is the sad truth. And if we find life, which I think we will in my lifetime, it's not going to be around an exoplanet. It'll be within our own solar system, because that's sort of the first place to look and where we can study it. And there are missions throughout the solar system that are upcoming. So, yes, sir.
What sort of technology develops this search that has yielded results that has helped do things at home?
So the question is, how is any of this useful to you, right? Right, unlike, last week or 2 weeks ago when it was, in the loop with poop, where you could see, immediate results. Here it's a little bit more subtle. So a lot of the technology developed for the, more advanced cameras and chips, that'll translate into better imaging technology here. But a lot of that, it's not necessarily done first in astronomy, right? It's one of a line of things that are ongoing. So it's hard to pinpoint any sort of direct results. It's sort of in tandem that people happen to be working on better charge coupled devices, these CCDs, that can then be used in astronomy or used in some medical imaging or what have you. So nothing directly obvious. Yes, sir.
Okay, I was just curious here. One of the reasons, I'm sure you're familiar with this, is that we know that Einstein's general relativity applies to the real world. That the orbit of Mercury, there's a precession in it that's induced by that relativity effect, that happens to what's there. And this is a lot closer. Jupiter's are a lot closer to the gravitational source. Are you seeing anything interesting going on as a result of being in a strong gravitational field that may be informing things about black holes or whatever?
Right. So the question is, do we see any effects of strong gravity on these planets? And the answer is we don't have enough data, right? For Mercury, right, you can see its orbit like at all times, more or less, right? And you can track it very precisely. Whereas here, right, we can sort of see it going around the planet every so often, the star every so often. But there's just not enough data there yet to say anything concrete. There was a question in the back.
With the new technology in computing, are there building any better satellites to get better feedback?
So the question is, are we building satellites to go further out with better technologies? So we have satellites upcoming. I was talking about this with someone at the break, that are upcoming that will do a better job than existing missions, right? So some of you may have heard that the Kepler spacecraft is currently paralyzed. So it's not, its ability to point with its reaction wheels is limited. So its mission has actually changed dramatically. But we have upcoming one mission that both Harvard and MIT are involved in, is TESS, the Transiting Exoplanet Survey Satellite, which will go, and its job is to stare at these smaller stars, right? Because if you're around a smaller star, the same size planet, if it's a little planet, will make a bigger dip than if it was a bigger star, right? So you can look for less subtle changes. And it's actually going to go, and instead of pointing at a fixed patch of sky, which is what Kepler did, it'll orbit around and it'll actually see every part of the sky at some regular intervals. So that's one that it's using, slightly different technology. You can say more advanced if you like, but also it's just a sort of different survey strategy to try and find these other planets. And then there's also the James Webb Space Telescope, which is the successor to the Hubble telescope, which will be launched in the future and which will again do sort of a better job from space and sort of continuously. And that will also not just help with looking for the dips in light from transits, but it will be able to do some of the chemistry and studying atmospheres and that kind of thing. All right, I think I'll take like 1 or 2 more questions and then the rest of you can come down and ask me, so everyone who wants to run away can do that. So, yes, sir.
Does the size of the star have any bearing on how likely the star is to have exoplanets? In other words, are they more likely to occur on certain size stars, or do they occur in all sizes of stars?
So the question is, do certain kinds of stars more easily or less easily have planets? And the answer is probably yes. So bigger planets, bigger stars are like the big kid on the playground, very boisterous, like getting into trouble, whereas the little kids just sort of quietly sitting there. And so actually the big stars, they end their lives earlier than the smaller stars. And so because they're more active and sort of things are, well, they're not necessarily more active in the way you might talk about stellar activity, but just the brightness of light coming off of them and things like that makes them a little bit less likely to have stars rather than smaller stars. Like stars are classified sort of from big to small in various other ways. So the biggest ones are called O stars and the smallest ones are M, well, you can get smaller than that, but like M dwarfs or M stars are more likely to have planets, we think, than like an O or an A star, which are the bigger ones. Yes, there was someone else. Oh, you all want to run away now. Okay, great. So we'll stop there. If you haven't already and are interested, you're welcome to take a star chart for the month of May. That you can have however many you want because May is almost up. Nobody's upset. The postcards only if you plan on cherishing it. And I forgot to mention this earlier. Lots of people kindly pointed out to me, if you are under the age of, I don't know, 25, you're welcome to take a sort of bigger, broader pamphlet that tells you about the solar system from the Chandra Observatory. I mentioned this because I have maybe 10 copies of it. So thank you for being such a great audience. You've asked really good questions, and I hope you'll come and learn more at future events. Thanks.